Welcome to this lecture series. In this lecture, we look at the notion of countable sets, or more precisely, the notion of countably infinite sets. All we need to know is basically the language of sets and functions and relations, maybe, and what we discussed about infinite sets. So we defined an infinite set as a set X which has the property that there is a proper subset of it which is in bijection with X. So it is in some sense self-replicating. So that's the definition, but then we looked at various criterions of infinitude. So we saw that a set X is infinite if there is an injection from naturals into it, if and only if, that's an if and only if statement. We saw that if X is an element in a set X and X is infinite, then X is in bijection with this thing, and so on. We looked at many things. So let's continue. Here are some problems for practice. This problem is perhaps particularly important. It's very easy, but I would say it's important, and perhaps it's best to solve it for certain before one proceeds. In general, whatever problems I pose are all very well thought out, and I want you to solve all of them. But the ones I mark with star are particularly essential. Okay. So what is a countable set? So a set S is said to be countable, or more precisely, countably infinite. So a set S is said to be countable if there is a bijection between the naturals and the set. So if X is in some sense a copy of the natural numbers, we'll call it countable. So what is a bijection? A bijection is just a device to relabel the things. So if you can relabel the natural numbers, make them look a little different, then whatever you get is countable. Okay. All right. So here is an example. Any infinite subset of the naturals is countable. Perhaps I should take this example later, maybe somewhere here, but let's take them in this order, the order in which I have prepared the lecture. So an infinite subset of naturals is countable. I will not write a gory detailed proof of it, but here is the main idea. Suppose we have some subset X of the naturals, which is infinite. So X is infinite. Then define N1 as the smallest element of X. And here what we are really doing is invoking the well-ordering principle. The well-ordering principle says that every non-empty subset of the natural numbers has the smallest element, so it is legitimate to ask for the smallest element in X. That is N1, and then inductively you define N2 as the smallest element of this punctured thing, right? And N3 as the smallest element of doubly punctured thing, and so on. So you get the idea. This will continue. And once we have that, let me shift these things below. So this continues, and now we can define a function from n to x as f of k is nk for each k. So I hope we get what we are trying to do. Basically, we are listing out the elements of x in increasing order, and once you do that, clearly it does look like a copy of the natural numbers. This is the formal construct. So then f is a bijection and we are done. So this is a bijection. Just check that this is a bijection, and that finishes the proof of the fact that every infinite subset of the naturals is a countable set. Before we proceed, let me give a warning. In literature, many times, countable means either a finite set or a countably infinite set. But I will not use that convention. For me, a countable set will always be the way we defined it. Okay. So for the next example, in fact, this is something that I should have taken first. So the whole numbers, this is the set of whole numbers. This is the set of whole numbers. So it is just the natural numbers union the number 0. So we want to say that is countable with a garbled spelling. So what do we need to do? We need to create a bijection between the naturals and the whole numbers. And that is very easy. Just define this function as that. And that is a bijection. You can easily check. So the whole numbers are countable, and somewhat more interestingly, the integers are also countable. I don't know what is wrong. Why are my spellings not complete or garbled or something? So the integers are countable. Again, we need to construct a bijection between the integers and the natural numbers. So here is how we do it. Define a map like this as follows. So we will say this is equal to n by 2 if n is even, and minus n minus 1 by 2 if n is odd. So it is a function which takes integers to natural numbers to integers. That much is easily checkable. This is an injective function because for every even number it gives you a positive answer, and for every odd number it gives you a non-positive answer. This is 0 when n equals 1, otherwise this is negative. Okay, so it is mapping the even numbers to positive integers and odd numbers to non-positive integers. So that much is clear, and on even integers this is injective, and on odd integers this is on even natural numbers this is injective, and on odd natural numbers it is injective. And since it is not messing up even with odd, this is an injective function. If that did not make sense, you can prove it for yourself. So this is an injective function. Why is it surjective? Okay, so let's look at the image of the even naturals. The even naturals are 2, 4, 6 and so on, and by the recipe, the way this function has been defined, they will be mapped to 1, 2, 3 and so on. So all the positive integers are covered in the image of the function f. And if you look at the odd integers, odd natural numbers 1, 3, 5, 7 and so on, their images under f are 0, minus 1, minus 2, minus 3 and so on. So all the non-positive integers are also covered in the image of f, and hence f is a bijection, and therefore the set of integers is also countable. Okay, so nothing very complicated going on. So what we will do is develop a slightly more convenient criterion to help us prove countability of various things. So the definition of a countable set is something that is in bijection with the natural numbers, but this lemma this theorem that we are going to prove looks slightly easier to use in practice. So we will show that a set is countable if and only if, first of all, it is infinite, and that there is a surjection from naturals to it. So to check if a set is infinite is very easy. Generally, it doesn't require much thought. And to create a surjection is far easier than creating a bijection. It requires far less care. Okay, so we need to prove this statement, and here is the proof. Okay, so first, suppose if we have a countable set, suppose your set was already countable, then clearly it is infinite, and clearly such a surjection exists because such a bijection exists. So this direction is trivial. We will prove the other direction. So assume we have a set such that, so X be an infinite set, and we have a surjection. What we want to do is we want to create a bijection between the naturals and the set X. Okay, so here is what we will do. For each element X in the set X, let choose, let nx in the fiber above X be chosen arbitrarily. What are we saying? Here what we have is we have a set, we have the set of all the natural numbers, and here we have the set X, and we have this function. Okay, we have this function, and for any point little x in the set capital X, what we can do is we can take the fiber above it, meaning all the points which map to it. So the set of natural numbers will be partitioned into fibers. This is a very general set theoretic thing. If you followed my lectures on sets and functions as present in this playlist or in the playlist Kickstart, then you know what I'm talking about. And anyway, that is a prerequisite to this lecture series. So we partition the set of naturals into fibers, and you just pick any element from the fiber that is above X. So there is the fiber above X, meaning all those points in the naturals which map to X. From there, you make an arbitrary choice. You just pick an element in that fiber, call it an X. And if arbitrary choice is something that you do not like, you can get rid of arbitrariness by choosing the smallest element in the fiber. But that doesn't really matter for us. You just pick an element in the fiber. Now, this set, call it S. This is an infinite set, is an infinite subset of the natural numbers. Why is it infinite? Because X is infinite. For each X, there is an element chosen in the fiber above X, and since two different fibers are disjoint, this is an infinite set because X is an infinite set. So we have an infinite subset of natural numbers, and hence S is countable. Thus, S is countable, as we saw in the previous slide. Okay, and now the map define phi from X to S, taking X to NX. This is a bijection. That is clear. This is a bijection. And finally, if you have a set X in bijection with a countable set, then the set is also countable. So this is a trivial fact that we did not state in the previous slide, but maybe I will note it here. If a set is in bijection with a countable set, then the set is also countable. Think about it. It is a trivial statement. It's basically a corollary of the fact that the composition of two bijections is a bijection. So we are just using that fact, and we have constructed a bijection between the set X and a countable set, and hence the set X is countable. So we will now take this theorem for granted. Perhaps we'll just use it without warning. Okay, so this has some corollary. So it says that a set is countable if and only if, first of all, it is infinite, and there is a surjection from a countable set to it. So instead of n, we just have a countable set here in this statement. And this is immediately clear because a countable set is just a proxy for natural numbers. So this should not be anything confusing at all. Once you have a surjection from a countable set to something, then you also have a surjection from naturals to something. All that is going on. You have, suppose, a countable set, call it whatever, call it Y, and you have a surjection to a set X. Then all you do is you compose it with the bijection, with any bijection that you have with the naturals and Y. There is a bijection between naturals and Y because Y is countable. So this composite gives you a surjection from naturals to X. That's all. But you can figure out the details if it is unclear. All right, so lastly for this slide, we see that an infinite subset of a countable set is countable. Again, in the previous slide, we saw that an infinite subset of naturals is countable. Here we are just replacing naturals by countable. And again, since countable is just a proxy for naturals, this is something that you can take as an exercise. So all of these facts we will kind of take for granted. With that, let us move on. So here is a lemma which says that union of two countable sets is countable. We will prove a more general version of this very soon, but let's see this. So suppose X and Y be countable sets. Suppose X and Y are countable. Then we want to show that X union Y is countable. WTST stands for want to show that. Okay. So, there are many ways to do this, but here is one way. First, we have a bijection between X and N. This is a bijection. So let me not write the full statement. I'll just say Bij to mean bijection. And we have a bijection between N and Y. Call it G. Using these two bijections, we need to create a bijection between naturals and the union of X and Y. Okay, so first we will modify the first bijection with here. So this set E, we will define the set E as all even naturals. E is all even naturals, and O looks very bad, but what do I do? O is all odd naturals. Okay, so here we have a map from E to naturals, which we will denote by phi. What does it do? It takes N to N by 2. So this is an injective map. Sorry, this is actually a surjective map. This is in fact a bijection, sorry. So this phi is a bijection. It is injective and surjective. Every natural number is in the image of it. So this compound thing is now our bijection of utility. Call it capital F. This is a bijection, and similarly we will modify the other guy. Here we have odd numbers, and this time we will choose odd number going to, what should we do? We should perhaps add 1 and divide by 2. Yeah, that should work. So this is N plus 1 by 2. Yeah, so this is this is also a bijection. We will call it psi. So phi, psi, F, G are all bijections, and this composite map we will call capital G. Okay, so F and G, meaning capital F and capital G, are bijections. Okay, now we have this set E union O, which is nothing but N, and this map to X union Y, which just takes, which first of all we should give it a name, perhaps H. So what is the definition of H? H takes N to F of N if N is even, not F of N, capital F of N, if N is even, and capital G of N if N is odd. So that is the definition of H. And since capital F is in particular surjective and capital G is in particular surjective, it is clear that H is surjective. H may not be injective, so that should be very clear, because, one should note this because X and Y could have things in common. So H may not be injective, but it is surjective. So thus H is a surjective map. And finally, this is an infinite set. Once you have an infinite set and you take union of it with something else, you again get an infinite set. So this is an infinite set on which there is a surjection of naturals. The natural numbers surject onto it. And as we saw in the previous slide, if we have a surjection from naturals to an infinite set, then this infinite set is countable, and hence this union is countable. So the last line you can write down, and that finishes the proof. So union of two countable sets is countable, and that you can use to again see why the set of integers is countable, because the set of integers is the set of naturals union all the non-positive integers. This is clearly countable, and to the countability of this you can easily establish. This is basically the set of whole numbers with everything with a minus sign, but the set of whole numbers is countable as we saw. So the set of integers is also countable, being the union of two countable sets. Okay. So this is actually super interesting. This set, what about Cartesian product of n with n? It looks like that if you draw it as an infinite matrix. Every element can be listed out in an infinite grid. This is also countable, and this is quite a surprise. I mean, when I first learned it, I was definitely surprised. And indeed, this fact was perhaps first discovered by Cantor, George Cantor, or G. Let me just say G. Cantor to be safe. A sufficiently troubled mathematician of his time, but he had made some remarkable discoveries which today is a part and parcel of all mathematics. Okay, so why is this countable? So this one, the proof I will not write down, but I hope I will be able to explain why this is countable. So the first most natural attempt to prove this would be to somehow, go in this direction. So you map the first natural number here, the second to this, third to this, but then this won't be a surjection. Ultimately, what we want to do is create a surjection from the naturals to this set. Because we already know that this set is infinite, all we need to do to prove that this is countable is to create a surjection from naturals onto this. So a natural attempt would be to start like this, but that will not cover any of the elements present here, and that will not be a surjection. So Cantor's brilliant idea was to rotate this figure by 90 degrees. Sorry, not 90, but 45 degrees that way. So let me not rotate the figure, but rotate our point of view. So you map the first natural number to this guy, the second natural number to this guy, the third to that guy. So we are traversing this way. We are not going that way. We are traversing that way. So the f of 1 is that, f of 2 is this, f of 3 is that, f of 4 would be this. This is f of 5, this is f of 6, and so on. So you can keep going, and it should be clear intuitively that you will cover the entire thing. This will be a surjection from naturals to it. In fact, this will be a bijection because the mapping is injective. But I'm sure you are convinced. So yeah, this is an amazing fact that this thing is countable. Okay. This is called Cantor's diagonalization argument. This is a kind of a restatement of the above. If x is countable, then so is x cross x. Again, if x is countable, it is practically the set of natural numbers, and hence this statement is same as that statement. Okay. So this leads to a very important theorem, is that if we have a sequence of countable sets, right, we have infinitely many countable sets, but they are indexed by natural numbers. So we have countably many countable sets, then their union is also countable. Again, this was quite a surprise to me when I first learned it. We just learned that union of two countable sets is countable, but here we are saying a lot more. We are saying countable union of countable things is countable. Or union of countably many countable things is countable. A fantastic fact. But the proof now is very, very simple. So define, so for each, first of all, for each I in naturals, let Fi from naturals to Xi be a bijection. Such a bijection exists because Xi is assumed to be countable. And now define capital F from n cross n to this union, which may be written this way for brevity. So by this notation, I just mean x1 union x2 union x3 union ... So we define this map as f of I comma n is equal to fi of n for all, of course, for all natural numbers I and n. So this is our definition of capital F, and the point is that capital F is surjective. Why is it surjective? Well, once you fix this, once you freeze the coordinate here and vary over the second coordinate, it is basically the values that you get are same as the image of Fi, but the image of Fi is Xi. So Xi is contained in the image of capital F, but this is true for each I, therefore the entire union is contained in the image of capital F. So this finishes the proof. I mean, we have a surjection of a countable set to this set, and this set is infinite because each Xi is infinite, so this set is definitely infinite. But we have a surjection from a countable set to this, and hence this set itself is therefore countable. So that's one line that I'm not writing. You can write it. Right. So very nice. Countable union of countable things is countable. Lastly, I think this is where we will finish the lecture. We will see that the set of rationals is also countable. So why is that? First of all, this is countable because it is a countable set cross a countable set. So this is countable. This you can fill the details if you like. Then this is countable because again this is a countable set cross a countable set. This is an infinite subset of a countable set, and hence this is countable. Or you can prove it in any way you like. But this is an infinite subset of a countable set, and hence this is countable. So that is also there. And lastly, we will finish with the proof that the rationals is countable. If you try to imagine the rationals and imagine the natural numbers simultaneously, it doesn't seem to fit in our vision that you can have a bijection between naturals and rationals. There seem to be far more many rationals than naturals. But no, that is not true. And this is what we are going to show, but this is very, very clear from what we have discussed. Just define a map F from this set to the rationals as the map which sends A comma B to A by B. This is a surjective map. This is not an injective map, but this is a surjective map. So we have a surjective map from a countable set to an infinite set, and hence this infinite set is countable. That's it. So very nice proof of the fact that the set of rationals is countable. And lastly, this begs the question, all of this discussion begs the question that does there exist an infinite set which is not countable? Does there exist an infinite set which is not in bijection with the natural numbers, which is in some sense strictly bigger than the natural numbers? And if you've been following Joe Rogan's podcast, then I think this has been mentioned countless times in that podcast. He's constantly getting his mind blown by the fact that there are many, many infinities. Some infinities can be bigger than the others. It's not some magical mystery. We will prove this in the next lecture. That no, the answer is no. There exist infinite sets which are not in bijection with the natural numbers, which are therefore in some sense strictly bigger than the natural numbers. And especially what can we say about the set of real numbers? To answer this will take some time. but we will be able to answer this very soon. Okay, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.